This is part 3 of the series Three-Dimensional Solids. And before we move on with any new work, I just wanted to make a couple of statements about the last problem that we worked on. First is that I wanted to reiterate the importance of saving your intermediate values. I mentioned that when we recorded this value, but I didn't say anything about the area of the base here. Anytime you calculate an intermediate value, it's important that you take these values and store them in your calculator and use the calculator values, not this truncated value here. And the reason for that is these trigonometric functions are approximations. And so when you round an approximation and you use that to get another value, you can tend to compound your error. So just to make sure that you're not off by a certain set of fractions, you want to make sure that you store your intermediate values. And it's up to you how you want to do it, but I generally tend to circle the value that I store the value in. So in this case, I stored my value in B here. And so just so that you know, it's important that you store your intermediate values all the time and use those values instead of the rounded values. Okay, next what we're going to do is we're going to talk about lateral and surface area of cylinders. Here we have a cylinder, and just as we did with the prism, I want to break this down into its constituent parts. So here we have the base. This is one base of the cylinder. This is a second base. This is the lateral surface. This curved surface connecting the bases is the lateral surface. This segment that connects the centers of the two bases is called the axis, and that is also the length of that segment is the height of the cylinder, and this segment from the center out to the edge of the lateral surface is called the radius. In order to get a clear idea of how this object is broken down, it's important for us to take a look at the net of this shape. So that's what I want to do, is use a piece of dynamic software to take a look at how this thing is broken apart. Now here we have a cylinder with the bases and the lateral surface, and I want you to pay special attention to how this thing breaks apart as we open it up. Notice that the lateral surface separates and created a seam here, and as it unwraps, pay attention to how this piece goes around the base. So as we unfold this, you can see that this distance from here to here had at one time wrapped all the way around the circumference of the base. So when we fold it back up again, you can see that coming together. So if I change the orientation, you can see how that unwraps. And you can see that as this unfolds, this linear distance here, from here to here, is the same as the distance around the base, which makes this distance the circumference. And again, if you take a look at from the side, you can see that this distance is the height of the cylinder. So as we unfold it, this length of this seam is the height of the cylinder. And so you can see what this guy looks like. So let's go back and let's put some details to this. So as we unfolded this lateral surface, it becomes this rectangle, where this distance is the height, and this distance is the circumference of the base, which is simply 2 pi r. And these, of course, are two circles, and the circles have a particular area formula. So when we want to find lateral surface, we're actually finding the area of this rectangle. And when we want to find the surface area, it's the area of that rectangle plus 2 times area of the base, just as we had with the prism. In summary, we have lateral area, or LA, is the circumference times height, the circumference times the height, which is 2 pi r h, and the surface area is the lateral area plus to big B. And remember, big B was the area of the base. That's the same for prisms and cylinders as well. So big B is the area of the base, so lateral area plus 2 times the area of a circle, which is pi r squared. And that's area of the base. So this big B is area of the base. Let's go ahead and take a look at an example and see if we can figure one of these out. Here we have our cylinder. The cylinder has a height of 6 centimeters and a radius of 5. Let's go ahead and start by finding the lateral surface. That would be lateral area equals the circumference times height. So circumference, which is 2 pi r h, which is 2 pi 5 times 6. So that is 5 times 6 is 30 times 2 is 60 pi, which is approximately 188.5. That's supposed to be a 5. Okay, now the surface area is the lateral area plus 2 times area of the base. So this is going to be approximately L, that's the variable I stored this lateral area in, plus 2 times pi 5 squared, which gives us a total of, now before I go ahead and total these, I'm going to set my B, I'm storing the big B in the calculator as 157.1. And so down here I can use my variables L plus 2 big B. So this value is stored in my calculator as this. This value was stored in my calculator as the L. And so surface area is lateral area plus 2 times B. And you can see that I have the approximate values because these are decimal approximations and not exact values in terms of pi. Okay, let's go ahead and work another example. In this example, we have a composite solid. The solid is made up of two pieces. We have a cylinder with a radius of 7 and a height of 10. And out of that cylinder, we've cut a rectangular hole with dimensions 5 by 4 inches. Now, to calculate the surface area of this, we're specifically going to have to look in detail at the lateral area first. The lateral area is going to be the area of this outside surface plus the lateral area of this rectangular prism inside. Think of this as finding the area of all the surfaces exposed to the air. So you can see this back surface here, this lateral face here, this lateral face here, and the front lateral face. So we're going to add the lateral area of this rectangle, or this rectangular prism, to the lateral area of this cylinder. And that's going to be the lateral surface area of this shape. And then when we find surface area and we're dealing with this area of the base, we're going to take the area of this circle and subtract off that area of the hole, which is the length times the width of this rectangle. So let's start out with the calculation for the lateral area of this, and let's first do the lateral area of the cylinder. So we have lateral area, we'll call that lateral area of cylinder, is circumference 2 pi, radius is 7, times the height, 10. So that's the lateral area of our cylinder, and we'll figure out where to store that in a second. To that, we're going to add the lateral area of this prism. So let's call this lateral area of the prism, and that's going to be the perimeter times the height. And you can tell that the height of this prism is the same as the height of the cylinder. So this is going to be perimeter times height, which is 5 plus 5 plus 4 plus 4. So that's going to be 18 times 10. For our total lateral area then, down here I'm just going to enter one string calculation, which is going to be the sum of both of these. So it's 2 pi 7 times 10 plus 18 times 10 is 180. I could have done the same here, but I didn't. And I'm going to store that in the variable location L. So we'll have this value in our memory location L. Now we could focus on the area of our base. So big B is going to be the area of this circular base, so it will be pi 7 squared, minus the area of this rectangular hole. So let's do that. This is going to be pi 7 squared minus 4 times 5. So that's the area of one of the bases. And we're going to go ahead and store that calculation in big B. And now we're ready for our full surface area calculation. So surface area is equal to the lateral area, which is what we had stored in L. So I'll just call that up, plus 2 times area of the base. And we'll be calling that up out of the calculator. Now this value came out to about 619.8, and this value comes out to about 133.9. And so if we add these together, we get approximately 753.8. That wraps up our discussion on lateral and surface area of cylinders. Let's move on to the next topic. In this problem, we're being asked to describe the effects of doubling the linear dimensions on surface area. Now, the best way to deal with these types of problems, rather than going ahead and calculating all this stuff out, let's just take a look at the formulas themselves. Here's the formula for surface area. It's lateral area plus 2 times area of the base. Lateral area is 2 times pi r(h), and the area of the base is 2 times pi r squared. Now, if we double each linear dimension, that becomes 2 pi times 2r times 2h. So we've doubled the r and we've doubled the h, plus 2 pi times 2r, and that quantity is squared. What that works out to is we take these 2 times 2, pull that 4 out front, and we have 4 times 2 pi rh. That's what we have in this side if we pull out this 2 times 2. On this side, 2 squared is 4, and r squared is just our original r squared from this equation. Now you'll notice both of these two have a 4 in their factor, so we can pull out that factor of 4, and what we have left, when we divide this expression by 4, we have 2 pi rh, plus divide this factor by 4, we have 2 pi r squared. So you can see that the overall effect on surface area is to multiply it by a factor of 4. So the effect of doubling linear dimensions on surface area, factor of 4. The only difference is the factor of 4. Well, that'll wrap it up for this part, and I will talk to you in the next video.